Chapter 6 starts with this idea of radian measure. Radian is another way of measuring angles. And the way that you measure a radian is that you put a circle on the coordinate plane with its center at the origin. Then you align an angle in standard position so the initial side is along the x-axis. The way that you measure a single radian is you look at the distance of the radius of the circle. Then you measure that distance along the edge of the circle, so it'll be the exact same distance. The angle that's created is called 1 radian. 1 radian is approximately equal to 57 or so degrees. It's not exact. Radians are used to describe and analyze circular motion because it's built upon the idea of a radius of a circle. The conversion for degrees to radians and radians to degrees is actually quite simple. To go from degrees to radians, you multiply by the ratio pi over 180. To go from radians back to degrees, you multiply by 180 over pi. And we actually will take a look at why that works. The equivalences are shown here. This is what we call a unit circle, meaning that the radius is a single unit. And this circle is divided into commonly used angle measures, and it's given in degrees and in radians. It's a very good idea to have these memorized or have some way of rationalizing this information. Tying in with radians is this idea of arc length. This distance that's measured along the edge of the circle is called an arc. So in order to determine the arc length, an arc length is represented by an S. What we want to do is we want to take the radius of our circle and multiply it by how many radians are around the circle. The idea here is that theta, which we've been thinking of as our degrees, has to be represented in radians. One of the biggest mistakes that students make is that they are given some theta in degrees and they work with that value rather than converting. You absolutely must convert this to radians before you actually start doing the calculation for arc length. So let's talk very briefly about why this works. If we have some circle with radius r, we can recall the formula for circumference of that circle to be 2 pi r. Well, the arc length, if we go all the way around that circle, the arc length S is the same as the circumference. So if we've got a unit circle, then the arc length is 2 pi. What that tells us is that there are 2 pi radians in 1 revolution, or in 360 degrees. So when we use that conversion factor, what we're saying is there are 2 pi radians for every 360 degrees, which reduces to pi in 180. Or we can say there are 360 degrees in 2 pi radians, or 180 degrees for every pi. That's where this information comes from. Next component that we'll look at is the area of a sector. When you have created some angle within a circle, that particular region, it looks almost like a triangle, but it isn't, is called the sector of a circle. So it's like a slice of pie. What we can do is we can actually calculate the area of this sector. So you can think of it like this. If the angle has a measure of theta, then what we're saying is that theta over 2 pi radians is what makes up that particular sector. If we think about the area of a circle, we know the formula to be pi r squared. So what we can do is we can say, well, I want this proportion of this amount. So what that gives us is theta over 2 pi times pi r squared. And when we reduce this, we end up with 1/2 theta r squared, or 1/2 r squared theta. Again, this big important piece, theta absolutely must be in radians. So let's do a couple of problems. We've got 3 separate angle measurements that we are going to convert to radians. So I will start with 108 degrees. To convert to radians, I will multiply by pi over 180. I can simplify this. 9 goes into both. This is 12 and 20 times. 4 goes into this. 3, 5 times. So that would be 3 pi over 5. Taking a look at the next one, negative 135 degrees. Again, because we're converting to radians, we multiply by pi over 180. Again, 9 goes into both of these. So this is negative 15. That's 20. 5 goes into both. Negative 3 and 4. So this is negative 3 pi over 4. Notice the angle was negative to start with, and I left it negative when it was in radians. The last problem, 325.7, we will again multiply by pi over 180. For this problem, I'm not going to leave my answer in terms of pi, and the reason is because there's no way to simplify this without having decimals. The rest of them simplified into very neat fractions in terms of pi. This one won't. So I will just plug this whole thing directly into my calculator. And I get 5.685. Notice that when I'm using radians, I don't actually write radians next to it, and I have not put a degree symbol next to it. This is sort of a rule of thumb. If there is no degree sign or there's no units to the angle, you will assume it's radians. This next set we're going to convert to degrees. Again, if you can notice, each one of these are listed without units. That's how I know that they are in radians. So if I'm converting 2 degrees, I'm going to multiply by 180 over pi. One of the ways that I think about this is that if I'm going from radians to degrees, what I want to do is eliminate pi. Pi is in the numerator, so I have to multiply by something where pi is in the denominator. When I put this into the calculator, 11 times 180 divided by 12, I can put it all in one line. I get 165 degrees. The next one, negative 7 pi over 6. Again, I multiply by 180 over pi. And again, pi's cancel. When I put this into the calculator, negative 7 times 180 divided by 6, I get negative 210 degrees. Same as before, because this started out as a negative angle, I need to represent it as negative even in the converted form. The last one, we might not think about it as being in radians because we don't see pi attached to it. Radians do not always have to be in terms of pi, but we still multiply by 180 over pi. And again, I put this exact expression into my calculator, negative 2.92 times 180 divided by pi. When I do that, I get negative 167.304 degrees. You can either leave it as decimals or in degrees, minutes, and seconds, depending on the problem. For this one, we're going to look at two separate circles. First circle has a radius of 25.6 centimeters, and we have an intercepted arc with 7 pi over 8. So what I need to think about with regards to 7 pi over 8 radians. Remember how we said there are 2 pi radians in a circle? That means that there's pi radians in half a circle. And 7/8 is just under half a circle. So it'll be like this. What we need to do is find the arc length. Arc length is S, and S is equal to R theta, as long as theta is in degrees. So that's 25.6 times 7 pi over 8. Plugging that into my calculator, I get 70.372 centimeters, meaning that is the length of this arc along the circle. Taking a look at the next one, same radius of 25.6. But this time I have an angle of 54 degrees. Well, remember the rule, theta must be in radians. So the first thing I have to do is convert to radians. Nine goes into this 6 times and 20 times. 2 goes into this 3 times and 10 times. So in radians, this is 3 pi over 10. From there, I can go back to my formula. So S is equal to 25.6 times 3 pi over 10. And I get 24.127 centimeters. Please keep in mind that for either one of these, we could have very easily left it our answer in terms of pi, and in order to have done that, we would have multiplied 25.6 times 7 divided by 8, and the answer we would have gotten would have been about 22.4, and then we just tack pi onto the end of that. Same thing with the one I did in blue. You would do 25.6 times 3 divided by 10, and you would get 7.68, and then you would tack pi onto the end of that. So last problem, so we have a circle. Our radius is 15.2. We have a central angle of 108. And we want the sector area. First thing I have to do is convert from degrees to radians. So 9 goes into this 12 times and 20 times. 4 goes into this 3 times and 5 times. So that would be 3 pi over 5 radians. So sector area is 1/2 r squared theta. So that's 15.2 squared times 3 pi over 5. I will again put this exact expression into my calculator. I might even convert that 1/2 to 0.5, but I will put everything else in exactly the way that it is written here. This gives me 217.750 square feet because it is an area.